Hey, everybody. Today we're going to talk about reactor plant materials. This will be one of a couple of modules, maybe three, but at least two modules. The first thing you need to understand is that when we're talking about metals, we're not just talking about solid lumps of matter. I have some like this. Uh, this isn't just a solid lump of matter. This is a collection of atoms arranged in repeating patterns. That repeating arrangement is called crystal structure. It's got a crystalline structure. It's an orderly, repeating, three-dimensional arrangement of atoms in a material. So this matters because the way the atoms are packed controls how easily the material deforms. Because of how these are packed, I can't deform these very easily. In fact, this is an anvil used for setting snaps in leatherwork. So this is designed to be, it's hardened, it's very, very, very non-deforming. It's not ductile. It's probably very brittle. But how these atoms are packed controls how easily it deforms, how strong it is, how ductile it is, how brittle it is. And the three major crystal structures we have are BCC, FCC, and then something called HPC or HCP, sorry. And so you'll get used to what these are and what these mean. We'll start with BCC. The BCC means body-centered cubic. FCC means face-centered cubic. HCP means hexagonal or hexagonal, however you want to say it. I say hexagonal, but I tend to say things wrong. Hexagonal, close packed. So BCC, starting with this one, has atoms at the cube corners. So we got the cube corners, and you'll see the better pictures in your materials. So refer to the pictures on the slides. And one in the center. So if I have a whole cube, right, with these different, and then one in the center. And so this is the crystalline structure for the BCC. Now it's not on the face; it's in the center of the cube. FCC, something similar, has atoms at the cube corners and one at the center of each face. So I don't think that's going to translate very well here, but I'm going to try and draw. So I've got all these, like if I had a die and I had something on each face and not just in the center. Well, there's the hexagonal HCP has layered hexagonal packing arrangements. So you need to know these geometries and you need to know their behavior. So as far as behavior, FCC is the most ductile. FCC is most ductile. That means it has really close packed planes and what's called slip behavior. It has an easier slip behavior. BCC is strong and has moderate ductility, but it can become brittle at low temperatures. BCC brittle, BCC brittle. How do we remember FCC is ductile? FCC like the airplane. Airplanes have ducts, ductile. FCC airplanes ductile. There you go. HCP is strong, but it doesn't slip a lot. HCC has limited slip. It's the least ductile, and this is one of the most important comparisons in the module. If you understand that FCC equals the easiest slip and the best ductility, you will answer several of the questions correctly. Let's pause here for a question. All right, now talking about grains and boundaries and creep. This is fun. When molten metal, so we pour a bunch of molten metal into a crucible, or from a crucible into a mold. The metal cools and crystals start forming all throughout this metal as it's losing its heat, as it's cooling. at once. Like as soon as it starts cooling, crystals start to form, these crystalline structures. And these individual crystals that form are called grain. So if I have a container of molten metal and I start getting crystalline structures, as it starts to cool all throughout it, these grains form. And then more grains form and more grains form. And as it cools and cools and cools, they eventually meet each other. So as this grain structure grows and this grain structure grows, eventually they meet. So what that looks like right there is these two grain structures meet and have a boundary. And this boundary right here is the grain boundary. A grain boundary is not a crack. That's not a crack. A grain boundary is not the outside surface. A grain boundary is on the inside of the metal where two different grains oriented in different directions, two different crystalline structures meet. So the grain boundaries matter because they affect strength and corrosion behavior. They can strengthen a material by blocking what we'll learn is called dislocation movement. Basically it acts like a roadblock that makes slip harder. And slip is where if you listen to the podcast episode, you should have a really good idea of ductility and slip and all those terms. But they can also become weak or chemically active regions where corrosion or creep damage may get in there more easily. So, and the grain size matters. Fine-grained metals have a lot more grain boundaries. They'll have a lot more of these boundaries where these different grain structures come together. And they tend to be harder. They tend to be stronger. Whereas coarse-grained metal tends to be softer and more ductile. So and this is all controlled by the heating and cooling rate. So this is why cooling rate and heat treatment change properties. Rapid cooling tends to create a lot of small, fine grains. Slow cooling tends to create larger grains. And like I said, those grain structures can inhibit slip, can strengthen a material and make it stiffer, basically. And so a lot of really fine grains due to rapid cooling can make it make it stronger, make it less likely to be ductile. So now what is creep? Creep is slow, permanent deformation under constant stress. Well, think about this and think about a nuclear reactor. Slow, permanent deformation under constant stress at elevated temperature. Our reactor plants, the reactor vessel, the core vessel, is under a constant pressure, over 1,000 psi, and high temperatures. It is extremely susceptible to that creep. So don't confuse creep with sudden fracture. Creep is time dependent. It builds up over time. And the three biggest factors for creep are temperature, stress, and time. So in reactor systems, all the piping, other high temperature systems associated with the reactor, such as the main steam system, this idea of creep matters because these components under load can slowly deform, slowly weaken, and eventually fail. All right, let's pause here for a question. All right, now let's talk about something called polymorphism and uranium phases. So polymorphism means a material can exist in more than one crystal structure while keeping the same chemical composition. What's a good example? Water and ice. In metals, this is called allotropy. And uranium is the example we're going to talk about because this is talking about nuclear power. So uranium has 3 solid phases. And these, I'm going to give you the names of these phases. This has nothing to do with the type of radiation. Okay. They just picked 3 Greek letters. So these phases are alpha, beta, and gamma. Each phase has a different crystal structure, and those crystal structures change its properties. So alpha uranium, the alpha phase of uranium, if we set this to room temperature down here, so say 70 degrees Fahrenheit, let's say Celsius, let's just say 25 degrees Celsius, because this is in Celsius, from up to about 668 degrees. So up to 668 degrees Celsius, this is alpha phase. Beta uranium, the beta phase of uranium, exists from 668 degrees Celsius up to 74 degrees Celsius. This is the beta. And then gamma exists from 774 degrees to its melting point, and I forget what that is, but 774 degrees and up to its melting point, and this is the gamma. Again, this isn't radiation. This is just the types of, or the phases. Alpha has an orthorhombic structure. Beta has a tetragonal structure, and gamma has a BCC structure. If you remember BCC, we talked about that. That's that body-centered. So you don't need to memorize all the details of those, but you just need to know which phase causes the main problem. And so the key point for us is that alpha phase prevents pure uranium from being an ideal fuel. So if we had a reactor in the alpha phase, it has poor dimensional stability, it has uneven thermal expansion, it warps, it distorts, it cracks, which is why we convert our uranium into uranium dioxide. We convert it into a powder so that it has a stable form where it's not going to experience these warping and distorting and cracking as temperature changes. It's a lot more stable in its uranium dioxide form. So it's the alpha phase that gives us the most problems. All right, let's pause here for a question. Let's talk about alloys and alloy microstructures. An alloy is where we just mix two or more elements where at least one element is a metal. So they don't have to both be metals to be an alloy. That's why they have hybrid materials. So you can mix a metal with something else and have a metal something alloy. Alloying is used to try and get the best of both worlds. We try and use it to improve strength, hardness, corrosion resistance, and performance at temperature. The basic thing is, compared to pure metals, alloys are generally stronger and less ductile. They also usually have lower conductivity. So in this module, we have three major alloy microstructures. The first is a solid solution alloy. Solid solution. And the alloying atoms completely dissolve into the base metal's crystal structure, which is extremely effective. So they may replace the base atoms or fit into the gaps. Either way, that distortion strengthens the metal. A second microstructure when we have an alloy is called a precipitate alloy. And in that structure, small hard particles form within the metal as it cools or as we heat treat it. Those particles block the dislocation movement, and they also increase strength. The third is kind of a mechanical mixture. In fact, I think that's what I called it. What it's called, mechanical mixture. So in a mechanical mixture, the phases don't completely dissolve into each other. They remain physically mixed as distinct phases, and then that final material combines the characteristics of both. So let's talk about two major desirable properties of something called Type 304 stainless steel. 304 stainless steel is highly corrosion resistant and has a high strength and a high toughness. 304 stainless is an FCC, face-centered structure, highly ductile, but the main desirable property is corrosion resistance and toughness. By room, corrosion and toughness. All right, let's pause here for a question. All right. This is a big section. There's a lot of stuff to cover here. We're going to talk about slip, stress, strain, and deformation. So slip is the primary mechanism of plastic deformation in a crystalline metal structure. Slip happens when atomic planes, so the planes in that metallic structure at the atomic level, slide past one another under shear stress. And shear stress is, do I have a good example of shear stress? I have a stack of magnets here. And shear stress, if I'm pushing on one side of this stack of magnets, I'm applying a shear stress that might move those top layers. This is actually, if I had this all unpackaged, this would be a good example. So as I'm pushing on these magnets, they're deforming across layers, and that's because of the shear stress. So just imagine at an atomic level. So the sliding doesn't occur all at once, it occurs through dislocation motion, and the easier slip occurs, the more ductile the material tends to be. So that's why, if you remember which one's more ductile, FCC, that's why FCC metals are generally more ductile than BCC or HCP. So let's talk about stress. So if I have a surface here and I apply a force to that surface, and this surface is 2 inches by 2 inches, so 4 inches squared. When I'm talking about stress, I'm talking about force per unit area, every inch squared. Strain is the deformation that's relative to that the original dimension. Tensile stress pulls and elongates the material. So tensile stress tends to pull and elongate the material. Compressive stress pushes and shortens, so compresses. Shear stress acts parallel to a surface and causes sliding. So if I have that stack, right, and I apply a force to this side, and then eventually it starts to shear, those atomic surfaces start to slide. Plastic deformation is permanent deformation. So we have two types of deformation. We have plastic and we have elastic. Plastic equals permanent. And an example, what's a good example? If I had something in here that I was able to, if I had some foam and I was able to apply enough force to that foam, or until it's permanently deformed. Oh, a rubber band. You can, you ever have luggage or something that's got those elastic straps on it to keep something like a pocket, and those wear out. And what happens is if one time it gets pulled to the point where it has plastic deformation and that elasticity doesn't recover. So plastic is permanent, elastic is reversible, is temporary. Elastic deformation is temporary. So to understand these, you have to understand a proportional limit and a yield point. The proportional limit is where stress and strain stop being proportional, right? It's the limit of the proportional, the stress and strain limit. And something called Hooke's law no longer applies. Yield point is where permanent deformation begins. So they're close, but they're not exactly the same. Hooke's law says stress is proportional to strain in the elastic region. So Hooke's law, stress is proportional to strain in the elastic region. Stress is proportional to strain in the elastic region. That means if you stay below that proportional limit where stress and strain, as long as you stay below that proportional limit where stress and strain do still matter, then the material will return to its original shape once that load is removed. But there's a limit. And if you move past its yield, now you're in plastic deformation, permanent deformation. So I know that's a lot. I know this is all a lot. Let's see. So slip. Slip is plastic deformation, and That's permanent deformation. Slip is where atomic planes slide. So once we moved, it's like when I pushed on those magnets, that magnet structure of magnets that stack, they didn't come back. I pushed them past their yield point, past their proportional limit. Slip happened, and it's plastic deformation. You need to know that stress equals force divided by area, force per unit area. Strain is change, how much change happened over its original shape. Tensile elongates, pulls, compressive compresses, shortens, and then shear is that sliding force. I think the biggest INC techs, this is all something you need to be aware of because we do use special sensors that measure tensile stress, compressive stress, shear stress, and especially on our turbines. So these are all terms you'll need to know and understand. And then proportional limit is stress and strain stop being proportional. Yield point is where the permanent deformation begins. And Hooke's law, stress is proportional to strain in the elastic region. Like I said, that was all a lot, but let's pause here for a question. All right. Let's talk about ductility, slip systems, and what affects ductility, which we already did a little bit. But ductility is the ability of a material to deform plastically before fracturing. So you can have elastic deformation, and then you broach into plastic deformation. But now there's another thing beyond plastic deformation, and that's the fracturing. So how far could you plastically or permanently deform a metal before it fractures? So ductility is the ability to deform plastically before fracturing. Yeah. And so a brittle material will break with very little plastic deformation. So if it's brittle, little to no plastic deformation. So in our reactor systems, we don't want things that are extremely brittle. We want things that are very ductile, that have room for deformation before it fractures. So ductility is important because ductile materials give us a little bit of warning before failure. That's why high ductility, high ductile metals are desired in our piping, our reactor pressure vessel, our fuel cladding, like all these things that see all this thermal stress and vibration all the time. And the slip matters here. More available slip systems generally mean easier deformation and greater ductility. Goes back to the FCC, that FCC metals slip most easily. Now, HCP, the hexagonal, has very limited slip systems at room temperature and is the least ductile, so it's not something we want to use as a metal in our structures. And then there's three main factors that affect ductility. Irradiation, which it turns out you get in a nuclear reactor, right? Radiation decreases ductility. Temperature. Increasing temperature increases ductility. The warmer a metal gets, the more ductile it gets, the more likely it is to bend and have plastic deformation before it shears. And then we have something called cold working, and that cold working decreases ductility because it increases dislocation density, it causes strain hardening. Cold working, imagine you're trying to make a knife or an axe from scratch, right? When you see them hammering on the metal, and it's not red hot, that's cold working. It's increasing hardness and strength, and it's lowering ductility. If you want to make a sword and you want to make it extremely strong and brittle, you want to do a lot of cold working. It lowers its ductility, but it's also you hit the wrong person on the head, can crack. That was a horrible analogy. So yeah, the ductility is where it deforms before it fractures. The slip systems, more ductility. That's where the FCC, that face-centered crystalline structure, comes in. If temperature goes up, ductility goes up. The more irradiation a metal gets, the less ductile it becomes. Did I say why? Because because the irradiation creates defects that block this dislocation motion. It reduces its ability to slip and causes embrittlement. And then the cold working causes ductility to go down. All right, let's pause here for a question. Let's talk about heat treatment and welding. Heat treatment. So this changes the properties of the metal by changing its microstructure through controlled heating and cooling. We've already talked about that a little bit, the idea that cold working a metal makes it stronger or more brittle. The big idea is that heat treatment can change hardness, strength, toughness, and ductility. Quenching, getting the metal really hot and then dumping it in a bath of room temperature oil, tends to increase hardness. Generally, when you increase hardness, you increase strength. And then we have another process called annealing. And this annealing tends to increase ductility. It also reduces brittleness. And temper a metal, it will reduce brittleness that's created by hardening. So annealing is where you allow hot metal to slowly come back to room temperature. If you put it in an oven or heat it up over, a long period of time, you can anneal metals, put it in an oven at 200 degrees Fahrenheit for several days. So that increases its ductility. It reduces those grain structures. It makes larger grains, helps those metal grain structures grow inside the metal. All right, welding is another topic because it can damage material if it's not controlled properly. Welding causes localized heating and cooling. It introduces residual stress, distortion, can cause things to crack or create a later cracking risk. So the common adverse effect is residual stress formation. And so things that we do in order to minimize that stress caused by welding, the welding stress, we preheat. We do after welding heat treatment. Controlled cooling. We make sure we're using the right weld designs. Stress relief annealing. You don't need to know a lot of those things. Just the main idea is that welding changes the local structure, whatever that grain structure is. At the point where you're welding it, you're introducing a lot of heat and you're changing those local structures and its stress states. So welding is complicated because you have to be careful with your preheating, with your cooling, to reduce the damage. All right, let's pause here for a question. Now, a topic we've talked about a few times, galvanic corrosion, but also we're going to talk about hydrogen embrittlement. So these are two big problems that nuclear power plants have. We get dissimilar metals. We get two different metals because we can't make everything out of the same metal. It's not ideal. And so when we get dissimilar metals and they're electrically connected in an electrolyte, one metal becomes anodic and corrodes faster, the other becomes cathodic and is protected. This matters in our material selection because if we use incompatible metals together that are going to be in water in a reactor, that can accelerate the failure mechanism. So the best way to remember this is dissimilar metals plus an electrolyte equals a galvanic concern. Hydrogen embrittlement is different. Hydrogen embrittlement is the loss of ductility and toughness caused by absorbed hydrogen. The material becomes brittle and more likely to crack suddenly. The two required conditions from your briefing sheet are the presence of hydrogen and a tensile stress in the material. Yeah, so for hydrogen embrittlement, I'm just going to write EMB, you need a tensile stress and you need to have hydrogen present, which makes sense, right? So zircaloy, because we've talked about this hydrogen steam reaction with zircaloy. Zircaloy 4, there's different zircaloys. And there's zircaloy 4, there's zircaloy 2. Zircaloy 4 is less susceptible to hydrogen embrittlement, because it contains less nickel. Lower nickel amounts in the alloy reduces its ability to pick up hydrogen, which reduces the hydride formation and makes the material less susceptible to embrittlement and cracking. So zircaloy 4, less nickel than 2, and therefore less hydrogen pickup. All right, let's pause here for a question. Overall, the most important things, there is more than just what I've covered here, but we covered a lot. Most important things are that crystal structure, right? Which of those crystal structures, BCC, FCC, HCG, that those control slip and ductility. The grain boundaries matter for both strength and corrosion. Like the more grain boundaries there are, the increased risk of corrosion we may have. And when we talked about uranium as 3 phases, alpha, beta, gamma, not radiation, that's just the Greek letters they used. Alpha uranium is the phase that makes pure uranium unsuitable as a fuel. That's why we have to convert it to uranium dioxide. And then alloys are generally stronger but less ductile than pure metals. And then stress and strain are technical terms that we use to explain how our metals deform. There's a law called Hooke's Law. It applies only in the elastic region. And then we talked a little bit about welding, galvanic corrosion, hydrogen embrittlement, and how they all affect material reliability in our nuclear power plants. If you get those, you'll do pretty good on the quiz. I strongly recommend you also listen to the podcast episode I posted. It's a little longer than the other ones I've done, but it's pretty thorough. Thanks.